One. Happy Monday. Today, I am excited that we come behind some really brilliant scientists. We have scientists over the past couple hundred years who have been able to solve all sorts of fascinating problems. And if you go into science, you'll be able to contribute to new ways of understanding the natural world around us, and it's pretty amazing. For example, scientists have come before us and done these standard hydrogen electrode experiments. They have collected standard potentials on a whole variety of materials, such that we can come along now and simply use this data and do something meaningful with it. As scientists in 2022, we can open up a table of standard potentials and simply compare two standard potentials and be able to predict what a new cell potential will be, simply by comparing these standard potentials. These standard potential values were collected by comparing all sorts of different materials under standard conditions, so 1 atmosphere of pressure, 1 mole per liter concentration, 25 degrees Celsius or 298 Kelvin, and we have all these half-cell potentials. Now they're written as equilibriums, so we can interpret them going from left to right to products or going from products to reactants. We simply need to pay attention to the sign and think about what we're doing with those half-cell potentials. Last class, we saw that we could calculate the standard cell potential for a redox reaction, like a battery, for example, by simply comparing the half-cell potential that's acting as the cathode, where reduction occurs, and comparing that to the half-cell potential of the anode, where oxidation occurs. Last class, we introduced the idea of the Daniell cell. It was one of the first batteries with zinc and copper. And we saw that the standard potential for that cell was 1.1 volts. This is the way that we can now predict that. People have done this experiment, they've collected these half-cell potentials, and now we can do something meaningful with that. At the cathode, we have copper being reduced. We did this last class, or that's where these scribbles are from. So that's plus 0.34 volts. And then from that, we take the difference with the half-cell potential at the anode. Well, the half-cell potential at the anode is zinc, and that has a negative 0.6 potential. That means it's kind of unlikely to go this way. Depends what it's being compared to. More likely to go this way. Since it's acting as the anode and we're taking the difference, that's minus 0.76 volts. You remember from math class, minus a minus is like adding that potential. And that gives us a 1.10 volts. And that's what we can read on the voltmeter. Now, you may have learned these as reduction potentials. And all these standard potentials are written as reduction potentials. So you could take the reduction potential and then add the opposite sign of the other reduction potential to make it an oxidation potential, and you get the same final number. The thing is, an oxidation potential doesn't really exist. It's just a potential. It's just what happens when we compare it to a standard hydrogen electrode. But by assigning the cathode, assigning the anode, taking the difference, we can calculate the cell potential. Now, for the iClicker questions today, we're simply going to be raising our hands. I prioritize not restarting my computer, so we're just going to be raising our hands today rather than risking a restart. We're going to keep going here. So be ready to raise your hand today. For this cell, we want to determine the standard cell potential. When we see that little degree sign, that tells us it's under standard conditions. It's a galvanic cell. It's going to hopefully occur spontaneously, and it's based on the following redox equation. Well, we know how to interpret this redox equation. Iron 3 plus to 2 plus is reduction. Iodine -1 to 0, that's an increase in oxidation number. That's oxidation. If we want to calculate the cell potential, we need to identify what's at the cathode and what's at the anode. we can look through that table in your workbook of all those half-cell potentials. And we can find the one that compares iron 3+ and 2+, and find the one that compares iodine and iodide. Now, they're both written as reduction equations, but they're equilibrium, so we can interpret them either direction. We have to identify which is the cathode and which is the anode. In the balanced redox equation, we see iron 3+ going to iron 2+. That's reduction. Reduction occurs at the cathode. We've identified that iodine is being oxidized, or iodide is being oxidized, and this occurs at the anode. So one reaction is going to go left to right, one is going to go right to left. But we don't have to do anything to these cell potentials. We're simply taking the difference. So the cathode minus the anode. And the difference is plus 0.24 volts. We just need to make sure that we're following our signs and being careful with our order of operations. Here, we're measuring something pretty positive, like plus 0.77, and something that's also fairly positive, plus 0.53. Both of those are more positive than the reduction of hydrogen, but we're simply taking the difference between these two positive potentials. So, question for you, chat with the person beside you. Given the cell diagram below, determine the standard cell potential. This time, we don't have an overall balanced equation. This time, we have to figure it out from the cell diagram. Chat with the person beside you, and then we're going to raise our hands. Okay, and we're going to put it to a vote. Who votes for A? B? C? D? Well done. Most people going for D, a few people went for C, and that's okay. That just means we had the signs opposite. But we're on the right track. So we need to identify the anode versus the cathode based on this cell diagram. Thankfully, it's always in alphabetical order. Anode on the left, cathode on the right. That means we have cadmium being oxidized at the anode and copper being reduced at the cathode. We can take those half-cell potentials and take the difference. Now again, this is under standard conditions, 298 Kelvin, 1 mole per liter. Okay, let's look at one more. Consider this voltaic cell. Let's see what's happening here. We have aluminum reacting with hydrogen ions to form aluminum 3+ and hydrogen gas. The aluminum, we can see, is going from an oxidation number of 0 to +3. That's an increase in oxidation number. That's being oxidized. Hydrogen, on the other hand, is going from +1 down to 0 because it's an element in its standard state. That's reduction. Okay, so the concentrations of these ions are 1 mole per liter. And this is important because this tells us it's under standard conditions. Later today, we're going to see what happens when you're not under standard conditions. The temperature is 25 degrees Celsius, and the voltmeter under these standard conditions is plus 1.66 volts. Without using this very handy table, which will actually give us the answer, predict the standard half-cell potential for aluminum. So we want to compare these half-cell potentials. We look at this balanced redox equation, and we say, well, what's happening at the cathode? What's happening at the anode? What's being oxidized? What's being reduced? We've already identified that aluminum is being oxidized. That means this is happening at the anode, which means aluminum is becoming Al3+, which means the hydrogen is being reduced at the cathode. Our goal is to figure out what that half-cell potential is in our table without peeking. Well, we know that the standard hydrogen electrode is our arbitrary reference point of 0. So without even looking this up, we know that the cathode value is going to be 0. What we want to solve is for this half-cell potential at the anode. Well, we now have an equation of plus 1.66 equals the negative value of what we're looking for. If I want to isolate this half-cell potential that for this cell applies to the anode, we simply solve for the variable. Therefore, the half-cell potential at the anode would be negative 1.66 volts, and then we peak and we say, yay, it's negative 1.66 volts. This seems like a relatively straightforward problem. The challenge here is simply interpreting what's happening. And problem solving in chemistry, the biggest part of it is just analyzing the problem and figuring out what's going on. What's the anode? What's the cathode? Is this spontaneous? Is it not spontaneous? Are these standard conditions, not standard conditions? Is this an electrochemistry problem or a Gibbs free energy problem or an equilibrium problem? And we're going to see today all those problems can be overlapped as well. Figuring out what's going on and then identifying what we need to do. Okay, so another raise your hand question. I mentioned this is linked. Let's see how it's linked. I'd like you to predict, before we chat about this, predict the relationship between Gibbs free energy and the standard cell potential. How do you think these may be related based on what we've chatted about already? Chat with the person beside you for 1 minute. Okay, and 3, 2, and 1. Who votes A? B? C? And I won't ask you to raise your hand for D. A is the correct answer. If we have a positive cell potential, then Gibbs free energy is negative. How would we know how that is related? Well, you may have noticed that for the reactions we were calculating so far, we had a positive standard cell potential here. And we had a positive standard cell potential here. These two reactions, well, 3 of them, were all spontaneous. You just set it up and it happens the way that it was written on the paper, going from left to right. So if we have a positive cell potential, if the cell potential is bigger than 0, then that reaction is spontaneous going from left to right, reactants to products. A battery, if you buy a AA battery, its cell potential will be positive. Your car battery has a positive cell potential. All these reactions have a positive cell potential because they happen spontaneously. And thankfully, in science, in our natural world, things make sense. We've already talked about Gibbs free energy and how to predict if a reaction is spontaneous, if it will go from the left to the right, more so than right to the left. We know already from Gibbs free energy that if we have a negative Gibbs free energy, that would give us a spontaneous reaction. How do we get a negative Gibbs free energy? Well, it's related to enthalpy and entropy of the system. If it's exothermic, that contributes to being spontaneous. If it has an increase in entropy, that contributes to it being spontaneous. If it increases the entropy of the universe, it definitely is spontaneous. And now we can correlate the cell potential to Gibbs free energy. So if something is spontaneous, Gibbs free energy is going to need to be negative. And we have this formula connecting these two big ideas. If the standard cell potential is positive, and we multiply it by F, which is Faraday's constant, a standard value of 96,485 coulombs of charge per mole of electron, and multiply it by the number of moles of electrons being transferred in this reaction, and we add this negative sign, that correlates the positive cell potential. We multiply it by a number and a negative sign, which makes the right-hand side negative to match a negative Gibbs-free energy. So this is how a negative Gibbs-free energy is spontaneous and a positive cell potential is spontaneous. We need to know that relationship. One is negative, one is positive, they're spontaneous. But now, multiplying it by the number of moles of electrons in the balanced equation, and by Faraday's constant, which correlates charge to moles of electrons, we can solve for Gibbs-free energy, which is pretty cool. We also know Gibbs-free energy is equal to negative RT times ln K. K was our equilibrium constant. And we know if we have a big equilibrium constant, that means the reaction lies to the right. So K and delta G and cell potential are all connected. Isn't that great? So chapter 4 is connected to chapter 3, which is connected to chapter 2. All these ideas come together. And we want to be able to understand what all of these values mean. Okay, so if we have a positive cell potential, it is spontaneous from left to right. If we have a negative cell potential, something can still happen depending on how the reaction is set up, but it doesn't happen left to right. It's going to happen right to left. It's going to go backwards. This is what we saw when we were calculating and seeing how all the standard potentials were collected. We got positive values and negative values. Negative just meant it happened the other way compared to what we wrote on paper. If the cell potential is 0, then that reaction is at equilibrium. If the cell potential of the battery in my stylus gets to 0, it will be dead. The reaction is now at equilibrium. We have no net driving force for the electrons, and I will have to replace the battery in my stylus. So another raising hand question coming up. This question here is simply calculating standard cell potential, but then interpreting the result. So this is on OWL. What I want to chat about is a little bit more interesting, and again, we're going to do this by raising hands today. Maybe I'll ask you next class if you raised your hands on Monday. How about that? Okay, a galvanic cell was constructed from 2 half cells. Zinc with zinc 2+, and nickel with nickel 2+. Interpreting this problem is the challenging part of the problem. For the reaction to proceed spontaneously, and now we know what that means in terms of Gibbs free energy and a positive cell potential, which electrode must be the cathode and which electrode must operate as the anode for this reaction to be spontaneous. Now, I've done part of the hard work for you already. I looked up these two half-cell potentials. When you're doing your homework, when you're solving new problems in your lab, when you're writing your final exam, you have to find these half-cell potentials. And it's a really big table, so it's worth practicing and learning how to find these half-cell potentials. And I've written a very handy equation that you should definitely know by this point in the course. So I'll give you 1 minute, chat with the person beside you. Which one must act as the cathode? Take 1 minute to discuss. Because it was hydrogen.
Why was this one 0?
Because that's hydrogen. By definition, it's 0. Okay, and we are going to put this to a vote. Which electrode must be the cathode? Which electrode must be the place where reduction occurs? Who votes for A? It must be zinc where the reduction occurs. Who votes for B? It must be the nickel. Well done. So that means everyone realized we needed a positive number here. How do we get a positive number when taking the difference? Well, we need something big and small. I want my biggest number to start and then subtract the smaller number, and that will give me a positive difference. Now, I have two negative values, and apparently that didn't trip any of you up. I used to get really confused. Back in like grade 4 when we learned negative numbers, I felt like my brain was breaking, and I actually got a little number line on my desk to help me try to figure out these negative numbers, which were eluding me. We have negative 0.25, like a negative quarter degrees in London, and negative 0.76, even colder if this was a temperature scale. So this one is big. This one is comparatively smaller. And of course, when we take that difference, the big number, even though it's negative, it's bigger, we subtract the more negative number. And of course, when we subtract a negative number, negative and negative turns into a positive. We have plus 0.51 volts. This tells us that it is spontaneous. That means negative 0.25 must be our cathode, which is why it must be nickel. Well done. Okay, one more voting question. This question, again, interpreting what's being asked is the interesting part, is the challenging part. This problem asks which of these metals, silver, copper, gold, tin, and iron, will dissolve in 1 molar HCl. Well, we haven't really, have we specified dissolving? I don't know. But it does relate to something we've chatted about already. If this is related to electrochemistry, we know something is reduced and something is oxidized. If metal dissolves, what's actually happening? Would it be reduction? Would it be oxidation? What would that half equation look like? So chat with the person beside you for 1 minute. Which reaction shows what's happening here to the solid metal? Okay, and 3, 2, and 1. We're going to put this to a vote. Who votes for A? B, C, D, E. Okay, and now you get to make 2 votes. We're going to vote again. You get to vote twice. Who votes for A? B, C, D, and E. Well done. So a metal dissolving means that it's going from a solid to a dissolved species, which is the aqueous, which is the charged cation. Metals don't really become negative, right? They tend to lose electrons. That's why A isn't the best option. We have to go with C, losing electrons. Well, if something loses electrons, that's oxidation. So this question is asking us, if we had a little chunk of this metal, I've drawn a nice little diagram to help illustrate this, very high-class drawing right here. We stick a chunk of silver in a 1 molar solution that's aqueous of HCl. And we say, does it dissolve? Are we going to lose some? Does the solid turn to aqueous? Is it oxidized? And then we do it again with copper. And then we do it again with gold, and so on. Based on what we know so far, we can predict what's going to happen, which is pretty cool. So the oxidation is going to be the metal dissolving. If a redox equation is happening, something else needs to be reduced. Here, I'm just going to tell you, well, it's the H+ ions that are going to be reduced. We need to think about what in the solution could hypothetically be reduced. Well, for this option, none of the metals are going to be reduced because metals don't really get reduced. So it could be the H+, it could be the H2O. H+ is a more positive half-cell potential than reducing water. So given the choice, it's going to be H+. And we're going to chat about this more in topic 4.3 come Wednesday. So at the cathode, the H+ ions from this 1 molar solution of HCl, that tells us we have H+ ions, chloride ions, and water molecules. That has a half-cell potential of 0. So we need, if this is going to be spontaneous, we need the difference between the cathode and the anode to be greater than 0. And we don't have the option of going both ways because we only have solid iron. We don't have iron 2+. So the metal can't really act as the cathode. It has to act as the anode. The difference between the cathode and the anode must be 0. The cathode has a half-cell potential of 0 because it's the reduction of H+. So we already know the first piece of this puzzle. Then we need to subtract the half-cell potential of the anode, and this needs to give us a positive value. 0 minus the anode must give us a positive value. Chat with the person beside you for 30 seconds. Based on that information, which of these metals will dissolve? 30 seconds, then we're going to vote on it. Okay, in 3, 2, and 1. Okay, let's start at the top of the list. Will iron dissolve? Put your hand up if you think iron will dissolve. Well done. Negative of this negative 0.44 volts. 0 minus 0.44 volts gives me plus 0.44 volts. Yes, that's a positive cell potential. Iron will dissolve. So if you clean your toilet with vinegar and you use a metal scrub brush, you are going to have a whole bunch of rust sitting in your toilet in a few minutes. Don't do that. Or just make sure you clean it up afterwards. It will dissolve in acid. Okay, what about the tin? SN, will it dissolve? Put up your hand. Yes, it will. For the same reason, it gives us a positive cell potential. What about the copper? Will that dissolve? Nope. Silver? Nope. Gold? No. There we go. Well done. Again, once we understand what's happening, it turns into a reasonably easy problem. But understanding what's going on is what I think is the challenge here. So when we see these types of problems, you have to break it down. What's happening at the cathode? What's happening at the anode? What do I need this cell potential to be? Do I know it's positive? Do I know it's negative? Or do I get to choose? And then how am I going to make that decision? Okay, well done. We've been talking about standard cell potentials. And we can take the difference from the cathode minus the anode and predict that cell potential. But what if we want to do an experiment or we want to design a battery that's not happening under standard conditions? What if we want the battery to work in London when it's minus 40 degrees Celsius? Or I don't need a whole mole per liter of that particular item concentration. How can we calculate the cell potential in real life when it's probably not under standard conditions? The way that we're going to do that is by starting our comparison between Gibbs free energy and Gibbs free energy under standard conditions. Standard versus non-standard conditions. And we saw this equation back in chapter 3, I think, topic 3.1. We could compare delta G under non-standard conditions to delta G under standard conditions by doing this nice little correction factor of the gas constant multiplied by the temperature in Kelvin and taking the ln of the Q. And you might say, ooh, I remember that Q, but what was that Q again? Remember, Q was just like K, the equilibrium constant, products over reactants to the power of their coefficients, but it's probably not under equilibrium. It's probably not at equilibrium. K only works when a system is at equilibrium. Q works anytime. It's probably not under equilibrium, or the battery would be dead. So we can calculate Q, the ratio of products over reactants to the power of their coefficients, and that can help us figure out where this system is at. So we're going to take non-standard conditions of Gibbs free energy, and we saw just a few moments ago that Gibbs free energy is related to the negative of that cell potential when we multiply it by the number of moles of electrons in the balanced equation being transferred and Faraday's constant. And we can calculate standard conditions Gibbs free energy using standard conditions cell potential, add the negative sign, and then the number of moles of electrons and Faraday's constant. So I'm going to take negative NFE and substitute that for delta G, negative NFE under standard conditions, and substitute that for standard condition Gibbs free energy. And then I'm going to divide everything by negative NF, just to give me a pretty equation. So divide by, well, I'll let you do that on your own time. Divide by negative NF. When I do that, I get this very handy equation that allows me to isolate for the cell potential, isolate for the standard cell potential, and then the negative NF is what divided RT ln Q. This gives us the Nernst equation, a very handy formula to be able to calculate the cell potential in real life. We can calculate the standard cell potential by simply looking up the half cell potentials in our table of values. And we know how to do that. We did like, I don't know, 3 or 4 examples of that today. This is kind of old news, important, but now let's extend it to non-standard conditions, when we have to consider the number of moles of electrons being transferred and what Q is at that moment. Well, for some experiments, if it is at 298 Kelvin, R is a constant, F is a constant, and if temperature is constant at 298 Kelvin, R times T divided by F is 0.0257. If our experiment under non-standard conditions is at least done at 25 degrees Celsius, we can use this handy little short form equation. So more often than not, I'm just going to jump to the short form so that I don't have to write R times T divided by F. But the official Nernst equation is on the left. So let's see how we can use this. It's kind of interesting. We want to find the cell potential of the Daniell cell. That's the zinc and copper cell that we've been analyzing a lot. And it happens at 25 degrees Celsius. But the zinc 2 plus ion concentration is 0.5 moles per liter. Moles per liter is molarity. And the copper 2 plus ions are 0.050 moles per liter. And we want to find the cell potential. But now we don't draw in that little degree sign because it's not under standard conditions, because the concentrations are not at 1 mole per liter. So if I'm working under non-standard conditions, I'm going to pull out my Nernst equation. I want to calculate the cell potential. To do that, I need to solve for the standard cell potential based on the half cell potentials from my nice table of values. I also need to figure out the number of moles of electrons being transferred in my balanced equation and figure out what Q is as well. Well, let's start with the simplest piece. I like working on jigsaw puzzles, and I started a jigsaw puzzle on the weekend. And I always start with the easy things. So I start with the border, and then I start with the most colorful pieces, and then it just narrows down the harder stuff if you do the easy stuff first. You have to do it anyway, so may as well start with the easy piece. So the standard cell potential is cathode minus anode under standard conditions. We have the overall equation here. We've analyzed it before, but I've included it again here just so it refreshes our memory. We can see the zinc is being oxidized. Therefore, the zinc must be the anode because the zinc is being oxidized. The copper 2 plus down to 0, that's reduction. That means this is the cathode. We've done this calculation already today. Plus 0.34 minus 0.76 gives us plus 1.10 volts. We've seen this number before, but this just reminds us of how to get that. So we now know the standard cell potential. The cell potential under non-standard conditions is going to be based on that 1.1 value, but then we need this little correction factor to account for the not standard conditions. Now I need to figure out the number of moles of electrons being transferred. Here I can go to the half cell equations or the overall balanced equation. Really, I need to go to the overall balanced equation because this is where the correct value is, but it's based on the half cell equations. Half cell equations, I can see 2 electrons and 2 electrons. So I'm like, I wonder if it's 2 electrons. I can go to this overall balanced equation. See, zinc is going from 0 to 2 plus. There's 1 mole of zinc and 1 mole of zinc. So that's a transfer of 2 electrons. Copper 2 plus down to copper 0, that's 2 electrons. In total, that means 2 electrons. We don't add them. 2 electrons are produced, 2 electrons are used up. The number's 2, not 4. If the coefficients were not 1, I would need to pay attention to the coefficients as well. So if there were 2 zinc, well, that would be 2 times 2. Or 4 zinc, I would need to multiply it by 4. So let's keep going here. Now I need Q. And again, this is just going to be a raise hand. What is Q for this cell? Chat with the person beside you for 20 seconds, and we're going to vote. Okay, and we're going to vote. Who votes for A? B, C, D, and most options for B is correct. We had to factor out the copper solid and the zinc solid, because remember, solid species don't show up in the K expression. This isn't a K, it's a Q, but it's the same idea, just not at equilibrium necessarily. So concentration of zinc ions over concentration of copper ions. Concentration of zinc ions was 0.5. This was given to us in the problem. Concentration of copper ions, 0.05 moles per liter. Now it just turns into an order of operations on your calculator. I would start with 0.5 divided by 0.05 equals, and then ln of the answer equals, and then keep that number in my calculator, multiply it by 0.0257 equals, divided by 2 equals, and then I would write it down so that I can double check my work when I double check my work. So 1.1 volts, that's my best guess when it's under standard conditions. But then we have to subtract this little correction value for not standard conditions. And therefore, the cell potential under these not standard conditions is 1.07 volts. It's just a little bit lower than what we would expect. And we could actually predict that it would be a little bit lower. It would be 1.1 if both of these were 1 molar, but they're not. But do you see how we have more product than reactant? Based on Le Chatelier's principle, if we have more product compared to reactant, it kind of shifts the equation back to the left, right? So we have more products than reactants. That means as the reaction goes to the right, it's kind of suppressed a little bit because we already have more product than reactant, which is why the potential is just a little bit lower than the standard cell potential. Okay, let's do one more of these interesting NERST problems. So we have a voltmeter connected to a cell. We're not given the overall cell diagram, or we are. We don't have the overall equation, but we can figure that out. The voltmeter reads plus 1.15 volts. And we need to figure out, well, what is the concentration of the cadmium ion? If we have a non-standard cell potential, we need to pull out this NERST equation, most likely. This time we're told the cell potential. We can usually, almost always, calculate the standard cell potential because we have these half reaction values. We could write the overall equation based on these two half cell reactions and based on this cell diagram to solve for N. We can figure that out, which will allow us to solve for Q, which is where the cadmium ions show up. So I'm going to break this into a few pieces, solve for the little question marks, where it just needs a little bit of thinking, a little bit of calculation to get there, to be able to go for my goal of solving for something in Q. Let's analyze this cell diagram. We always have the anode on the left and the cathode on the right. That means aluminum is my anode. The cadmium is my cathode. I can go ahead and calculate the standard cell potential because it's the half cell potential at the cathode minus the half cell potential at the anode. I've identified my cathode and my anode, so I can simply solve and take the negative of the negative 1.66, which in essence is adding that 0.1 or 1.66. This gives me plus 1.26 volts. Now notice that the electrons do not match up. If I want to write the overall equation, with cadmium being reduced, aluminum being oxidized, I need to find a common factor for these electrons for the overall balanced equation. But I don't care about the number of electrons when I'm calculating the standard cell potential. Here, do not multiply by the number of electrons. We certainly need to pay attention to the number of electrons when we come up with the overall equation to come up with n. That's important. But for the standard cell potential, it's not dependent on the number of electrons being transferred. So I can calculate this difference regardless of the number of electrons. But when we come back on Wednesday, we will calculate the number of electrons to find the overall redox equation and jump into 4.3. Have a fabulous day.